Good afternoon all, and welcome to the SIMM webinar that we're having on sampling for geometallurgy. I should introduce myself. I'm Megan Becker. I am the chair of the conference committee for the SIMM Geometallurgy conference that is coming up next month. And we are very delighted to have Tricia Scott with us today. Tricia has been associated with geometallurgy for quite a while and also involved with this conference series. And we are very glad to have her on board with us. She is the principal geomet estimation at Anglo American, where she leads the development and delivery of spatial geometallurgical models. Tricia began her career at Kumba Iron Ore, gaining experience across exploration, production geology, and geometallurgy before moving to Anglo American in 2021. Since then, she has provided geometallurgical support to global operations, including platinum, iron ore, and copper, with a focus on model development and implementation. So in the run-up for our conference, we like to have webinars increasing the profile of geometallurgy and attracting members right from around the world who are able to attend. And so we're very delighted that Tricia agreed to present to us today on a project that she's been working with the Global Mining Guidelines group. So I'm going to hand over to you, Tricia, and the floor is yours. And just, sorry, one more thing. We're going to take questions at the end of the seminar, the webinar. If you can post your questions under the Q&A, we will go through them when Tricia has finished her presentation. Thank you.
Well, thanks very much, Megan, and to the SIM for inviting me to present today on the work that we've been doing with the GMG. So let me just start the slideshow. All right, so thanks for joining today, everybody. Today I'm going to be sharing some of the work that we've been doing with the Global Mining Guidelines group on developing a guideline for representative geomet sampling. So the GMG, well, what I'm going to speak about today is firstly who the GMG are and a little bit about the antitrust do's and don'ts. I'll give you an introduction to the sampling guideline and an overview of what kind of information it contains. I'll go through a case study where we apply some of the principles from the guideline using actual mine data. Then I'll talk about how you can provide feedback to the guideline, and if you would like to contribute, how you can get involved in the future. Then I will end off with the next steps for the guideline before it's going to be published, and then there'll be a chance for some Q&A. So just a few pointers that we usually keep in mind when interacting with the GMG. I won't go through this into too much detail and I'll focus on the do nots. So basically, do not engage in discussions with competitors about prices, competitive information, anything that can be construed as collusion or reducing competition. Also, do not disclose any confidential or financial information about your respective companies. So we'd like to share knowledge and help each other learn from past mistakes, but without presenting any risk to our companies. So who are the Global Mining Guidelines Group? They are a Canadian not-for-profit organization dating back to 2005. They're funded by its members with 9 working groups, which are presented here on the right in these green and blue boxes. The working group that the Geometallurgy Guideline is part of is this mineral processing working group. They consist of a small core team with over 7,000 volunteers. So what they do is they tackle challenges raised in the working groups, and they manage each challenge as a specific project. Their deliverables consist of quite a range of products and depend on the task. So their deliverables include white papers, guidelines, case studies, webinars, short courses, as well as mine tours. So if anyone would like to learn more about the GMG, I encourage you to go to their website and have a look at the information that is there. So the committee that has been involved in the representative sampling guideline consists of about 30 contributors across 5 continents. There are a wide range of disciplines involved, including geomet practitioners, academic researchers, regulatory compliance experts, mining company representatives. There's participation from the consulting industry, and we've got international geographic coverage. So while we've had quite a diverse input into the guideline so far, it's important to hear the viewpoints of a variety of stakeholders, which is a big reason why I'm presenting here today. Peer review is essential in obtaining a robust guideline that is useful and can make a difference to the industry. So we're very open to hearing your ideas and any critiques or comments at the end of the presentation as well. So the project objectives of this guideline are to produce clear, actionable guidance on geomet samples and how to obtain representative samples. This covers sample selection, representivity, as well as management. The outcome will be a guideline document, as well as a few case studies using actual mine data. So why do we need to build this guideline? Well, firstly, sampling is not gambling. The samples that we collect result in data that are used to build a model that form the basis of many multi-million to multi-billion-dollar mining decisions. These decisions are made with the aim of optimizing and creating stable mining operations. So any questionable samples will result in a risk throughout the mining value chain. So flawed samples will result in flawed decisions and create hidden risk. Currently, there are no accepted standards across the industry. Every operation develops their own internal practices, and it's difficult to benchmark or compare across deposits. We've seen stakeholder confidence issues when it comes to geomet sampling, and regulatory compliance challenges are increasing. So this all means that we see a need for practical, actionable frameworks that people can use when implementing their own geomet programs. So how the guideline is structured is that we start off with with an introduction and a few definitions. This is followed by a section on planning. So we talk about resource allocation, scheduling, as well as constraints on the program. This is followed by selection rationale. So what samples do you collect and how do you select these samples? Why are certain samples collected? And then execution. So some advice on how to physically collect the samples, as well as some handling protocols. This is ended off with stakeholder engagement advice, as well as a few case studies, tools, and templates that can be used by the reader. So the bulk of the document focuses on the three sections I've highlighted in this box: planning, selection rationale, and execution. So the guideline is meant to be practical and implementable across a variety of deposit types. It's not prescriptive, so it won't go into a huge amount of detail into how each type of deposit can obtain representative samples. It's a framework that professionals can use to tailor-make their own geometallurgical programs, sampling programs. Okay, so I'd just like to clarify a few terminologies that I'll use in the presentation and that you will see in the guideline as well. Firstly, performance drivers are geological features that are most likely to impact the metallurgical performance being predicted. So this can be things like lithology, texture, alteration, as well as geochemistry and mineralogy. Focus case is the subset of the resource that needs to be represented by the samples. So typically we have a large mining area, sometimes a large block model covering it. The focus case is the subset of that area that we want to characterize with our geomet sampling campaign. So this could be, for example, the plant feed material that is planned to go through the plant over the next 5 years' life of mine. The sampling frame is the available drilling subset that the samples will be taken from. So for example, if this is a plan view of your drill holes on a grid, typically not all of these sample drill holes will be available for geomet sampling for a variety of reasons, either because of the drilling type, the age of the drill holes, etc. So the sampling frame is the drill holes that you will use to select your geomet samples. Just talking about the different types of data that you can use in a GeoMet program. We've got various types of data in geological, geometallurgical, as well as metallurgical programs, and they all vary in terms of metallurgical prediction accuracy, cost, and abundance. However, we want these different data types to complement each other so that they can be used to understand the metallurgical performance variability and how it relates to the ore body. So looking at this pyramid, we start at the bottom with the drilling database, where a large amount of data is captured on a variety of variables. From that, we build our geological model, where not all variables that are captured in the drill holes make it to the geological models, but it still provides a lot of data for our program. We've got proxy tests, which are simplified geometallurgical tests that can also provide a lot of important information on GeoMet variability. We've got simplified process tests, such as open batch tests. We've got simulated data, such as locked cycle tests and computer simulation. And then we've got operating data, which can be, for example, industrial or pilot plants. So at the top of the triangle, we've got few points because they're typically quite expensive, but they give an exact reference for plant performance. At the bottom, these points are typically cheaper to obtain, but we've got a lot of them. However, they're a poor reference for plant performance, but good reference for geological variability. So we move from what we want to do during our GeoMet program is connect metallurgical performance with ore variability, which is typically done through a GeoMet block model. So just to talk a bit about the theory of sampling and how it applies to GeoMet sampling, there are limitations and a few pointers that we can get from the theory of sampling. First of all, the theory of sampling typically addresses single variable problems, whereas GeoMet requires a multivariate approach. So with GeoMet, we want to move beyond grade-only selection approaches and consider the multivariate relationships in our data. Sparse sampling isn't easily addressed with the theory of sampling. However, what is useful is that the theory of sampling emphasizes appropriate sample collection, handling, as well as parameter determination and QA/QC. So all of this can be used to assess the quality of the primary and subsequent subsamples that are used for test work and assay. For example, where we collect a recovery sample that typically goes for head assay, flotation test work, and then tails and concentrate analysis. And I'll pick up where I left off. All right, cool. So I was talking about the theory of sampling. I think where I got cut off was when talking about comminution test work. So for comminution test work, the theory of sampling emphasizes a high quality primary sample. So we'll focus on obtaining an intact drill core with high total recovery, low fragmentation, and fines loss. But the limitation is that the actual core pieces that are taken for this test work aren't considered during theory of sampling. So what we mean when we're talking about GeoMet representativity, and what I'm going to focus on with our case study later, is that the samples need to accurately reflect the focus case. The performance drivers need to be sampled in the correct proportions. The full variability range of our performance drivers must be captured where they're numerical. We need to have appropriate spatial distribution. Sample integrity should be maintained, and we need to make sure that the tests are suitable the samples are suitable for the tests that will be conducted. And just a last mention on stakeholder engagement. So I think a lot of us know when it comes to geometallurgy, a large part of our job is collaborating across disciplines and breaking down long-established silos. So an important point is to involve stakeholders early and bring them along for the journey. Change takes effort, but if stakeholders are kept in the loop from an early stage of the GeoMet program, then it's easier to implement change and use the GeoMet results. We need to make sure that management expectations are aligned with what the program can deliver. It's important to listen, empathize, and make sure stakeholders understand each other. This is often easier said than done, but it's really important to make a concerted effort into understanding the various stakeholders involved in the GeoMet program, especially those outside of your area of expertise. Collaboration between geologists and metallurgists is essential, but don't forget the mining engineers. A mentor once told me that the role of geologists and metallurgists is quite obvious in the term geometallurgy, but mining engineers and mine planners play a crucial role in successful implementation of the program as well. So make sure they're involved from an early stage. So just making sure you're aligned with your stakeholders and that you've got good engagement will ensure that our deliverables are fit for purpose. Okay, so that's enough with the theory. Let's look at some practical examples and some actual data. So the guideline is quite long at the moment. It's about 60, 70 pages long. This is a very simplified case study, but using actual data to demonstrate some of the principles that we'll use in the guideline. Before I get started in this, I would just like to thank the company who provided this data. It's not always easy getting hold of data that people are willing to share, and it takes a lot of work to safely share a mining data set. So thanks to you guys, you're our real unsung heroes for today. So for context, we're in the early stage of a mining project where we want to focus on identifying the processing characteristics of the major geological domains and also anticipate any potential processing challenges. So we're at an established mine, the plant is already set up. We just want to understand the geomet variability. How we're going to do that is by collecting crusher work index data to understand the expected plant throughput rates and power requirements. But at the moment, we've established an interdisciplinary team with clear roles and responsibilities. We've discussed how resources will be allocated, including the personnel that are needed in the program, what equipment we'll use, what lab services are needed, as well as which labs will be used for the program, how the data will be managed, and also how we'll implement quality control throughout the process. We're also aligned on budget constraints, schedule requirements, and the performance drivers, which I'll speak about in the next slide. So early on in your sampling program, it's recommended to have a meet the deposit meeting where all of the stakeholders in your team can learn more about the local geology at the mine. So in this meet the deposit meeting, we're learning about the deposit Riverstar. This is a high-grade hematite deposit where hematite is defined as ore above 61% iron. It's also got some ferruginized shale, as well as a banded ironstone formation, or BIF. So on the right here, we can see, let me just get my laser. We can see a plan view of the ore body outlined in red and orange here. The gray dots are our diamond drill holes. So in the cross section here, we can see that at the bottom of the ore body, there is a laminated textured hematite, which is overlain by clastic textured. There is a little bit of conglomeratic in the blue over there, but it forms a very small portion of the total deposit. So typically, when you meet a deposit, you'll also talk about things such as structure, mineralogy, where do you expect to find the highest grades in the deposit, etc. So also bear that in mind, but I'll keep it simple for now in this case study. So our performance drivers are going to be lithology, so BIF, shale, and hematite. Texture is another performance driver, which is laminated, clastic, and conglomeratic. Geochemistry, it's sometimes difficult to know from the start which elements are going to control your geometallurgical properties, but this is the suite that's typically analyzed on our drill hole data, so we'll make sure that they're all represented in our sampling program. And then density is another important one. So typically the selection of your performance drivers is a function of things such as the geological understanding of the deposit, processing knowledge and experience, historical plant performance data, if there is any, statistical relationships between variables, and also just the judgment in what is likely to drive metallurgical performance. And during this meeting, the metallurgists will also discuss the expected plant process route and what they expect to be the typical performance drivers. So the data we've got available in this case study include drill hole data, where things such as geochemistry, density, lithology, and texture are recorded. We've also got geology solids or wireframes for the textures, as I've shown in these plots here. And we've got a block model, which contains information on lithology, textures, geochemistry, and density. So I'm going to present some focus case statistics. So as a reminder, the focus case is a subset of the resource that needs to be represented by the samples. If we look at our earlier data type triangle, this is the level that we're talking about now, where we're looking at the geological model data. So our focus case is for the next 5-year mine plan and for plant feed material, which consists of ore above 50% iron. In total, we've got 29 million tons of ore that is planned to go to the plant over the next 5 years from this deposit. Looking at some statistics, we've got about 32% of our focus case will consist of clastic textured ore. 64% will be laminated. A very small proportion will be conglomeratic. Got about 0.5% of BIF, and then a reasonable amount of shell, but 3.5%. So typically we aim to obtain 30 samples per expected domain. But because this is a relatively small deposit, only 29 million tons, I'm going to make my maximum number of samples 30 per domain. So I'll aim for 30 samples in the laminated textured ore, half that amount for clastic, and then a few samples in the conglomeratic BIF and shale. So even though, especially the conglomeratic, we only get a very small portion of this material that's expected to go through the plant, we must remember that the geomet sampling is also about risk reduction. We want to make sure that all ore types are sampled in our program, because often even a small amount of detrimental material can have a large impact on the process. So make sure you've got samples of even the small proportions. Just looking on the right here is the same data just presented as a bar chart. So we can see laminated is our most abundant rock type, followed by clastic, and then shale and BIF, and a small amount of conglomeratic. So here we're looking at our numerical performance drivers. This has again been filtered to just the focus case. We're looking at the 5-year mine plan and the ore that is above 50% Fe. So we can see the ranges of the block model in aluminium, barium, iron, potassium, manganese, phosphorus, density, sulfur, and silica. So the geomet samples that we select should cover this range of chemistry to make sure that it's representative. Looking at our sample requirements for the crusher work index test, we typically need about 10 to 20 fragments that are about 2 to 3 inches in size. The interval length that we'll send for test work will depend on what kind of core you've got available, if it's half core or whole core, as well as the availability, and the condition of the core. So we've got HQ sized core available, and it's half core. So we're going to aim for 5-meter composites, which should send plenty of material for the test work. We're going to focus on sampling within the performance driver boundaries. So for example, in this cross section where we've got laminated here, we can take 5 meter samples within that interval, 5 meter samples within the clastic interval, but we don't want to cross that performance driver boundary. And also remember that these must be consecutive samples down the drill hole, not compositing from various drill holes to make enough sample. So our sampling frame, this, as a reminder, is the drilling subset that's available and that samples will be taken from. And the sampling frame should represent the focus case. So in this image on the right, we've got the drill holes that are available for sampling. These were all drilled in the last 3 years, so we're going to consider them our sampling frame. What I will do is draw sections across each of these drill holes and then stagger the drill holes that will be selected for sample selection to create an image like this, where each of the gold stars represents a drill hole that I'm targeting for sample selection. After selecting my 5 meter composites, I'm going to reiterate through them to make sure that all of my performance drivers are represented accurately. So the final image will look slightly different to this, but this serves as a good starting point for making sure my samples are spatially representative. So the type of sampling we're going to use is systematic sampling. So this is where you define a fixed interval and collect samples regularly along that fixed interval. So in our example, I'm going to take 5 meter samples, along every 10 meters of the drill core. So it'll be a 5 meter sample, skip 5 meters, and then another 5 meter sample along these drill holes. The starting point should be randomly selected to avoid periodic biases, which is what we're going to do. The advantages of this systematic sampling method is that it provides good spatial coverage of the deposit. It's easy to implement and replicate, and it's useful for identifying spatial trends or gradients in the deposit. Limitations to be aware of are that it may introduce a bias if the sampling interval coincides with natural cycles in the deposit. We can also miss features that occur at a smaller scale than the sampling interval. So here it would be important to communicate with your geologist to make sure, to be aware of any features of performance drivers that might occur at an interval of smaller than 5 meters that could be missed. This may also not be optimal for highly variable deposits. So in the guideline, we've got some other methods that will be outlined, but for now, for this deposit, we are using systematic sampling. Okay, so looking at our Geomet sample stats, now we're looking at this level of the data triangle where we're looking at the simplified process open batch Geomet tests. So here we're analyzing for geological representativity. If we look at this bar chart that we saw before, in gray, we've got the block model proportions. In blue are the proportions represented by our Geomet samples. So roughly, we've got the Geomet samples present in the correct proportions with a large amount of hematite clastic and hematite laminated. Most of our samples come from the laminated texture. We've also got some BIF and some conglomeratic samples. Unfortunately, in this case study, I couldn't find suitable material for a ferruginized shale to create a composite. And this is something you might find in your Geomet programs as well. Sometimes we just don't have enough physical material for the test work. So here, when I look at my actual planned samples, I've got a 0 mark there for shale. This is a risk that should be flagged. In future drilling and sampling campaigns, we can target this material to get those samples. But also this risk should be communicated to the users of this Geomet data so that it can be accommodated for. And it can also be accommodated for when developing the block model. Okay, so these are the proportions I spoke about earlier. The number of samples that I've actually got now are 21 clastic, 33 laminated, 1 conglomeratic, and 2 BIF. So slightly more than what I'd planned, but present in the correct proportions. And this is what we're going to go out and actually collect from the drill hole data from the sampling frame. So looking at the numerical statistics, here we're aiming for geochemical representativity in our Geomet samples. So aluminium looks good. We've got the correct proportions. barium, iron, potassium, manganese, phosphorus. Relative density, or RD, is a bit of a tricky one. The sampling frame doesn't give enough samples for this 5 to 5.2 bin. So I've chosen samples that are as representative as I can to at least cover the range in densities that we can expect over the next 5 years. But this is another potential risk that we should communicate to the stakeholders and also accommodate that when using the data. Sulfur looks good, as well as silica. So overall, I'm happy with the geochemical representativity, just a slight risk with the density, which we need to communicate. So other factors that I'm going to consider are firstly the temporal representativity. So this you can see in 3D or cross-section. If you look at the mine plan over the next, for each year, for the next 5 years, you should get samples within each of those time periods so that your sampling program is representative through time. Spatial representativity is also looking good here. So this is the plan view of the deposit and the samples that have been selected in yellow. The blue cross-section here is represented in this cross-section. So we can see samples have been selected at varying depths as well as across strike of the ore body. Looking at the purple cross-section here at the bottom, here again, we can see representative samples through depth and across the cross-section. Looking here, it's just a 3D view of the samples we've selected, where we've got the exploration or the diamond drill holes in blue and the samples that have been selected for geomet test work in orange. So looking spatially, we can see we've got samples throughout the River Star deposit. And our spatial representativity is looking good. Then lastly, process-specific representativity, so making sure that the samples are suitable for test work. We considered the test work requirements earlier, and through the length of sample we're collecting, it should meet the requirements, but important to also bear that in mind when you're physically collecting the samples to make sure that the core integrity is up to scratch. Okay, so we've checked so in summary, we've gone through this high-level case study. We started off with establishing a GeoMet team aligned on sample program requirements, resourcing, and schedules. We had the Meet the Deposit meeting where we discussed the geological background of the River Star deposit and the performance drivers. We summarized the focus case characteristics. We identified our sampling frame, so the diamond drill hole data that we took the GeoMet samples from. And then we identified samples within the sampling frame whilst ensuring that they meet physical test requirements. We assessed sample representativity in relation to the focus case. So I'm happy with the representativity that we got and the results. The only thing to bear in mind is the lack of ferruginous shale data and the potential slight bias in density. So as the GeoMet program progresses, what we'll do is analyze the incoming data, comparing the results to what we expect. We will follow QAQC procedures and use adaptive sampling strategies that evolve based on an ongoing analysis of representativity. So if we see areas that are showing high metallurgical variability, we may want to adapt our strategy to obtain more samples there to properly understand that variability. And then lastly, consider expert and peer reviews. We're all human and we all have biases that we might not be aware of. So about peer review and getting either external experts or peers from other areas of the company to review the GeoMet program is always a good idea. So that's it for what I wanted to present about the guideline. This is just some information on how you can contribute if you would like to towards the guideline. There are multiple ways of getting involved, including providing anonymous case study examples. You could join a review committee to review a specific section of the guideline. You could share internal procedures that you find work for you. You could contribute industry data sets, as well as participate in various working groups. So Neil Edney is the right person to contact if you would like to get involved. His contact details are there, and we'd love to hear from you. Example data sets are something that we're always looking for. We prefer anonymized examples, but data that we're looking for and that you can contribute if you would like include drilling, block model data, metallurgical sampling databases for a complete deposit, sampling programs with outcomes, any failed sampling case studies that we can learn from, successful representativity demonstrations that show the value of a good geomet sampling program, as well as any document templates that you find very effective during your geomet program. So the next steps, we aim to have the draft sections available during Q4 2025. This is followed by an industry review period. And then we aim to have the final guideline published during Q2 2026. And during this period, we'll have multiple feedback cycles, presenting our results and obtaining comments and critiques, questions from our stakeholders or from potential users of the guideline. Yeah, thanks. That's it for me for today.
Thank you, Tricia, for that very enlightening presentation. I love case studies because they always make it look so practical as opposed to these philosophical things. So it was really helpful being able to see the case study and engage with it. So I'm going to open the floor for questions. If you could post your questions into the Q&A tab, we will be monitoring that because we can't monitor the chat and the Q&A at the same time. So if we can monitor that one, then we will get going. And the first question, which has just come up now, is, and I think I was also thinking the same, how do you determine the target number of samples by domain? You mentioned 30 per domain. What was the origin of that number?
Yeah, there's a lot of history behind that, but in brief, it's a commonly accepted rule of thumb when you're starting your GeoMet programs, that 30 samples is considered representative. You can get a good normal distribution per domain if you've got 30 samples. So 30 is generally what we aim for, but it does very much depend on how much variability you've got in your deposit. If you've got a very nice homogeneous domain, you can get all the information you need from 5 to 10 samples. But the more variability you've got, the more samples that you needed. So 30 is really a base starting point. Another rule of thumb is that you should have 1 sample per million tons in the deposit, which is why I reduced the number of samples I was collecting in our case study. We only had 29 million tons, so it didn't really make sense. I think we had 5 or 6 domains. It didn't really make sense to aim for 180 samples in a 29 million ton deposit. So it depends firstly on the variability of the ore body. It depends on how large the ore body is that you're targeting, or the focus case. It depends on how much variability your plant can tolerate. So if your plant is very sensitive to fluctuations in feed, you want to understand that variability very well. If it's less sensitive and it can handle those changes in feed properties, then you can get away with less samples. So yeah, and then lastly, another way to determine how many, yeah, okay, let me leave it at that. That's some general guidelines. Ore variability, how big the deposit is, and then plant tolerances to variability will determine it. But 30 is general rule of thumb that's commonly accepted, and it's a good starting point.
I'd like to encourage people to post questions while we're waiting for, can I just build on that some more? So is that 30, would you see that number changing? And are there any other rules of thumb for things like precious metals versus, you use the example of a bulk commodity like iron ore, so precious versus base metal, something. How would that number vary?
Yep, it would vary because you would typically expect your bulk commodities to be a little bit more consistent with regards to certain metallurgical properties. It depends. I'm trying to think. It depends on what geomet response you're measuring. For hardness and comminution, bulk commodities can still be quite variable, but I'm thinking if you've got a coal seam, for example, that is not going to be as variable as a porphyry copper deposit, for example, with many alteration events and different textures. So there would be differences between commodities, definitely, but it depends on what you're measuring. But yeah, I'm hesitant to say that bulk commodities are more homogeneous, but overall, on average, they probably will.
Okay, then the other one that also goes on the number of samples, is there a recommendation between the number of samples for testing versus samples for characterization?
So what do you mean by characterization? So a geological characterization then?
Let's ask Fernando, who posted that question. Maybe Fernando can just add to his question and we could go on to Richard's question. So the crusher work index provides a process design parameter for throughput. Was all characterization tests considered to provide information for the downstream flow sheet development early?
Okay, I suppose this is also all characterization, where I assume you're talking about geological characterization. So things like mineralogy, thorough geological logs, geochemistry characterization to understand the ore types from that point of view. Yeah, i.e. mineralogy. Yes, yeah, exactly. So definitely that's part of that data type triangle that I showed, where at the bottom, you've typically got a lot of geochemistry assays. If you've got mineralogy for majority of those drill holes, that would be great, because then you can look into establishing correlations or proxies between mineralogy and the ore property. In this case, crusher work index, we didn't have mineralogy available, so we worked with just geochemistry and the geology wireframes to obtain representativity. But yes, definitely mineralogy would be an important one if you have that data, to make sure that it's representative and to inform the flow sheet development. Okay, so just looking at the Fernando's question, also assuming he's talking about the same type of characterization. So yeah, if it's not always feasible, I would obtain as many sort of geological characterization tests as possible on the primary drill holes, because this will inform variability. If you can only sample half of it, that's still a great start, because it's more data than the geomet test work, the open bash test work. So if you can find a really good, a solid relationship between the geomet property being measured and mineralogy or other geological characterization data sets, then that will improve the spatial accuracy and the resolution you've got for estimation quite significantly. So that's also another really important point to keep in mind when designing your program, is you want to have those tests co-located where possible. So where you're doing flotation test work, hardness test work, make sure you've got chemistry on those samples, mineralogy on those samples, any other proxies that you could potentially investigate. So things like GeoPura, FTIR, all of those co-located in the beginning of your program so that you can assess those relationships and use them to characterize your deposit.
All right, thank you. So there was another one that popped up in the chat from Cecilia, and she's asked, to gather the stakeholders actors together, what is the most challenging task when it comes to agree about a sampling plan?
The most challenging task, which occurs, I think, in most relationships with people in general, is communication. We come from very different backgrounds. What a metallurgist calls a composite, for example, might not be the same thing as what a geologist calls a composite. So making sure you understand the terminology that's being used and aligned on that is probably the most challenging. Make sure you spend time rephrasing, understanding each other, and yeah, and properly understanding each other. Yeah, yeah, I would say that's. Let me just think. So with the sampling program, also generally we want a lot of data. That's another tricky point where there are budget constraints. So we've got to compromise on how much data we want or the optimal test work that we need to do for the budget constraints and also for the physical sampling constraints. So we might not have core samples that are large enough, for example, if the core was typically done on for purely exploration drilling purposes, smaller NQ sized core, that's often not suitable for the geomet test work. So communication and then any constraints, I would say, as well, some budget constraints as well as physical constraints when it comes to actually collecting the samples that are suitable for the test work.
All right. So we've also had a question from Kalen. He has asked, are there GeoMat guidelines for sampling processes further down the value chain, such as plant sampling, metal accounting, and tailings? These are, in my view, critical since they are often your reconciliation nodes.
Yeah, definitely a really good point. And I'm not sure if there are guidelines for plant sampling. That would be out of scope for this guideline, which is focusing on GeoMet, but there definitely should be. That's a really good point and something we should actually look into because it would be useful to reference those guidelines even in this one that we're collecting at the moment. So yeah, really good point. Thanks, Kellen. I'll have a look into it, but I'm not actually sure if those guidelines are available.
Perhaps I can also just add, I know that in terms of metal accounting, there is AMIRA guidelines on that. It would be interesting to see how they might connect with one another, I guess.
Yeah, definitely.
Then we have a comment from Cornelia. She said, mine is more a comment. The challenge is with the focus case. This can change. Sometimes you want to preload with GeoMate data so that the best decision of processing can be made. But then when the mine area is determined, your samples may not be representative anymore.
Yeah, yep, that is a very valid point. We often end up playing catch up because mine plans change. We've got samples in areas that aren't going to be mined anymore. We're focusing on a different area, prioritizing that one, and we've got to rush to get geomet samples in time. So yeah, that's definitely a valid point. What I would focus on there is, again, communication with the mine planners. What are the chances of the mine plans changing over the next 5 years, just so that you can minimize that potential risk by maybe just getting a few samples in areas that are being considered as a possibility over the next 5 years and not considering the current 5-year mine plan as gospel. So yeah, that's what I would do there. But it is very difficult if plans change and the focus case changes.
Just checking if there are more yet. How many operations do you think are already following such a model for sampling like you're recommending, just to get a feel for how different it is out there?
I think there are a few following majority of it. So quite a few following maybe about 80 to 90% of the guidelines in my experience. But I don't know, maybe Adam, if you want to comment on, I know you've got a lot of diverse experience as well. You might have a different viewpoint.
But I think that the people that practice this and are serious about it are following most of this. But I think that most people don't. So the people who talk about it do, but most people don't, if that makes any sense. So if you look at any particular 43-101 report or any feasibility study and things like this, there's usually pretty major deficiencies. And that's the reason why we're developing this GMG guideline, because there is no other document out there to describe how to do this. So that was the impetus behind developing this, because there's no established protocols or common practice. But I do agree that when you go to the conferences or the major internal guidelines for major companies and things like that, then they are following generally these principles that we're just documenting.
Okay. Thank you, Adam. Any last minute questions? Okay, so I would like to thank Trisha very much for giving us this webinar and taking up her time to deliver the webinar for us. As she's mentioned, there's lots of scope for anyone who's interested in contributing to the GMG guideline, specifically reviewing this guideline to be involved. I'm going to make a little punt for there's another working group that also looks at the guidelines for common data reporting, and that has also looked at things like how do we report flotation, comminution, leaching, mineralogy data. So that's also happening simultaneously to this working group. So if you would like to be involved, please do contact the GMG. If you also want to just talk more about geometallurgy, learn more about geometallurgy, we invite you to attend the SIMM Geometallurgy Conference that is taking place next month. Nasli, could you perhaps put the flyer back up for us?